All right, let's talk about probability. Now, this is so much more than just a chapter in a math book. It's really the fundamental tool that scientists use to get clear answers from a world that's filled with fuzzy, messy data. It helps them find that real signal hidden inside all the noise.
So that leads to a great question, right? How do they predict things that seem completely unpredictable? I mean, our world is just packed with randomness, everything from the weather to medical trials. Well, making any sense of it at all comes down to one thing. You've got to speak the language of chance. So let's dive in.
And believe it or not, the very same rules that tell you the odds of a dice roll are also helping physicists figure out what's happening inside these incredibly complex particle collisions at places like CERN. It's amazing, really. The scale is just astronomically different, but the core ideas of probability, they stay exactly the same.
So here's our game plan. We're going to start with what probability even is. Then we'll look at 2 different ways of thinking about it. After that, we'll learn the basic rules of the game. And then we're going to unleash the incredible power of something called Bayes' theorem to solve a real-world puzzle straight from particle physics.
Okay, so first up, what is probability? At its heart, it's not just some abstract math concept. For anyone doing experiments, it's a critical tool for planning and for making sense of data that's, well, always a little bit messy. To put it simply, probability is just a number we use to say how likely something is to happen. It's on a scale from 0 to 1. 0 means, nope, absolutely impossible. 1 means, oh yeah, that's a total certainty. Everything else, from flipping a coin to a star-going supernova, falls somewhere in between those 2 extremes.
Now, here's where it gets really interesting. Not everybody actually agrees on what that number between 0 and 1 truly means. And this philosophical split leads us to the 2 main camps in the world of probability. You've got the frequentists and you've got the Bayesians.
So if you ask a frequentist, they'll tell you that probability is all about what happens in the long run. If you could flip a coin 1,000,000 times, then a number of heads would get super close to 50%. That's its subjective probability. But a Bayesian thinks about it differently. For them, probability is a measure of your personal belief. I mean, think about it. When a forecaster says there's a 55% chance of winning an election, they can't rerun that election 1,000 times, right? That 55% is just their level of confidence, based on all the data they have.
This graph right here is the frequentist idea in a nutshell. It shows a student flipping a coin 1,000 times. Just look at it. The line is all over the place at the beginning, super chaotic, but as you get more and more flips, it settles down and gets really, really close to that true 0.5 mark. This is exactly what they mean by long-run frequency.
So, how does any of this actually work? Well, probability isn't just the Wild West. For it to be useful, it has to follow a few very simple, very logical, and totally unbreakable rules. We call them the axioms of probability.
A brilliant mathematician named Kolmogorov boiled it down to 3 ground rules. First, probability can never be negative. Makes sense. Second, the chance that something will happen out of all the possibilities is always 1 or 100%. If you roll a die, you're guaranteed to get a number. And third, if 2 things can't happen at the same time, like rolling a 1 and a 6 on the same die, the chance of one or the other happening is just their individual probabilities added together. Simple as that.
Okay, building on that, what if 2 events can happen at the same time? Well, to find the probability of A or B happening, we can't just add them up. Why? Because you'd be counting the part where they overlap twice. So the trick is, you add the probability of A and the probability of B, and then you have to subtract that little slice of overlap so you don't double count.
Now that we've got the rules down, let's get to the real powerhouse tool in our kit. This thing called Bayes' theorem. It's this fantastic formula that gives us a proper mathematical way to do something we all do intuitively every day. Update what we believe when we get new information.
But first, we need one more idea. It's called conditional probability. And all it is the probability of event A happening, given that we already know for a fact that event B has happened. See, knowing B happened shrinks our world of possibilities. We're not looking at everything anymore. We're only looking inside the circle where B is true.
And that one idea leads us directly to this elegant and really powerful equation, Bayes' theorem. It tells us how to calculate the probability of A given B by using the probability of B given A, plus their individual probabilities. It basically lets you flip a conditional probability around, which, as we're about to find out, is an incredibly useful superpower.
And here he is, the man behind the magic, the Reverend Thomas Bayes. He was an 18th century statistician and philosopher, and his work, which was actually published after he died, laid the foundation for an entire field of statistics. It completely changed how we think about evidence.
Okay, enough theory, right? Let's get our hands dirty. Let's see how Bayes' theorem helps real-life physicists solve a very real problem they face at a particle accelerator. Okay, so here's the scenario. When protons smash together, they create a stream of other particles. Let's say this stream is 90% things called pions and 10% things called kaons. Now, our detector is pretty good. It correctly identifies a kaon 95% of the time. But it's not perfect. It sometimes messes up and calls a pion a kaon about 6% of the time. So here's the million-dollar question. When that detector flashes and says kaon, what's the actual probability that it really is a kaon?
So how do we tackle this? We do it step by step. First, we just write down everything we know, the particle mix, the detector stats. Second, we frame our question in the language of probability. Third, we pick our tool, and this problem is practically screaming for Bayes' theorem. And finally, step 4, we just plug in the numbers and see what comes out.
And when you run all those numbers through the formula, you get this. The probability that a particle you detect called a kaon is actually a kaon is only 63.8%. Now stop and think about that for a second. Even with a detector that's 95% accurate at its job, a positive result is only about 64% trustworthy. That's a huge, huge difference.
And this right here is a perfect example of why probability is so absolutely vital in science. The raw data that spits out of an instrument is never the whole story. There are always these uncertainties lurking. Bayes' theorem gives scientists a way to quantify that uncertainty, to cut through the noise, and to figure out exactly how confident they should be in what they're seeing.
I mean, that result is just incredible. A formula cooked up in the 18th century is helping us identify subatomic particles today. It really leaves you with a big question, doesn't it? If the rules of probability can bring this much clarity to the weird world of quantum physics, just think of where else it could help us, from a doctor's diagnosis to the stock market to better understand the uncertainty that's all around us.